Welcome everybody, sorry for the delay. I'm going to do a presentation on PCANT. PCANT stands for Programmable Capture and Analysis of Network Traffic. This is work I've been doing primarily with Ludovic Noiry, but also with Mathieu Boussard and Nicolas Lesauze at the Enterprise Network Department at Nokia Bell Labs Core Research. So before I get into PCANT, a few words about me. Yes, there's about me written on the board. Since this is the presentation I'm doing as a new Links member, it's also a good occasion to know what I've been up to in the past years. So I've been on and off at Links from 2012 to 2018, working with a number of people in this room, namely, and then headed off to Nokia Bell Labs in 2018. And there I've been working primarily on 3 subjects. One of them is IoT&M, of which PCANT is a part. So I'll get into that. It's about the automated deployment of traffic not monitoring functions inside networks. I've also worked on Dispose, which is a multi-tenant approach to resource sharing for fog computing, network isolation, basically trying to get the IoT promise working where everybody is sharing their objects in a distributed manner so that everybody can use everybody's objects in a secure fashion. And then more recently with Ludovic, we started working on the quantum internet, and namely quantum routers, quantum router architectures and quantum network protocols. But today I'm going to be focusing on IoT&M and PCANT. So IoT&M stands for IoT Network Monitoring. It's the project, and PCANT stands for Programmable Capture and Analysis of Network Traffic, which is the solution we've set up. So what is the motivation behind PCANT? We've seen through research, through our interactions with research, a lot of algorithms come up, traffic analysis algorithms, with a lot of different intentions and aims. But most often we have data scientists doing their research, and then the test bed is a single router with 1 or 2 network equipments, and it never really gets pushed to actual networks. We're often running these algorithms offline. And it's a bit underwhelming. The primary reason behind this, oh dear, blue text isn't showing up at all, sorry. So the blue text for the first part is issue, and the second part is cause. So the primary reason we're not seeing these algorithms pushed to big networks, actual live networks, is because data scientists and network, network administrators are 2 very different jobs with different skill sets. And so what we're trying to do with PCANT is bridge the gap and say, we want data scientists who come up with new algorithms to be able to push them automatically on actual networks without having to do all the painful work of capturing the traffic inside the network equipment, which often requires some knowledge of network equipment and low-level Linux commands. So we want to do all that for them. And so they just push their code and they're monitoring the network. So that's where PCANT, the platform, comes in. The motivation for this came from a PhD with Nesrine Amar, supervised by Ludovic and Sébastien Tixoy here, where she had an algorithm, I'll show it later. And basically, they spent quite a lot of time trying it on the network, which wasn't the aim of the PhD. And we saw other people spending that much time doing the same effort, and we wanted to automate that process. So what are the key considerations when developing PCANT? Sorry. First, when you're doing live network monitoring, you need to capture the traffic at the network equipment level, but you often have very limited resources there, so you can't treat that traffic and analyze it locally. At the same time, you can't forward all the traffic you want to analyze to, say, the cloud where you're going to analyze it, because then you have bandwidth issues where you're clogging the network. So you need a trade-off. You need some way of extracting data from your traffic rapidly so that you have aggregated data to send to your cloud. And once in the cloud, you analyze it. The problem is what data you need extracted from the traffic flow depends entirely on what your model and your algorithm for analysis is. So we wanted to provide a solution where everybody can come with their analysis algorithm and say, this is what data I need extracted from the network and how I need it aggregated, so that we could leverage both capturing inside the network in real time without clogging the network equipment, without clogging the bandwidth, and at the same time have the compute power of, say, cloud machines. And of course, as I said, we don't want to have data scientists working with network equipment because that's often a bottleneck in our workflow. So,
Data scientists are the bottleneck.
Yeah, I've seen it happen a lot. Okay, so how does PCANT work? I'm actually going to show you the user workflow, what it means to use PCANT as a data scientist, say, as somebody who has a monitoring algorithm to deploy, and then I'll go more into detail about what is inside PCANT. So what we have, a bit far from the slides, is a platform, say, in the cloud somewhere. We have namely some compute power in the compute node, and then we have our network we want to monitor with our different network equipment. And we have our user on the left who wants to deploy monitoring functions. So he's going to send observer and analyzer code to the platform. So we have a REST API where they push the code. The observer code is there to say what data I want to extract from the network, how I want to aggregate it, and then push it to the cloud. And the analyzer code is actually your Python machine learning code, which we're going to deploy in the compute node. So these two chunks of code put together form what we call the blueprint of the monitoring algorithm. They aren't a monitoring task in and of itself. The reason for this is if you have, say, I'll show an example later, a task which for a given device, say a given MAC address, focuses on that device's traffic to do monitoring on that device, you could use that same code on multiple devices. So the blueprint is the code which could be instantiated on multiple devices. It's sort of a prototype of a monitoring function. And we're going to send that to a blueprint manager, which is going to store it for now. Once we've uploaded a blueprint, we're actually going to run a monitoring task. And for that, we're going to feed the system a blueprint reference, a blueprint we uploaded earlier, and parameters, say the MAC address we want to monitor, to the platform. And the platform is going to do all its automatic magic. So for now, we've been doing user things, but now this is where automation comes in. The platform takes that past data, retrieves the blueprint from the blueprint manager, and deploys the observer code with the parameters to the network equipment. So we have agents within the different network equipments which are running, which we've installed once, and which are going to receive the observer code, which is going to tell them how to extract data from the network. And these agents are going to deploy and start running that observer code inside the network equipment. At the same time, we're going to send the analyzer code to the compute node, and we're going to set up the analysis, which is going to start running. So at this point, we have code running in the network equipment, which is looking at the network traffic, capturing that traffic, filtering it, extracting relevant data, and aggregating that data and sending it to the compute node. And in the compute node, our machine learning code, which is receiving that data over time online and analyzing it. And all this is automated. So what that means is that the agents are tasked with retrieving data from the network. We don't have to worry about how that's done. As a user, we don't have to worry how that's done on the network equipment. Once the data is sent to the analyzer, same thing. We don't have to worry about where the analyzer is running. I don't have to think about complicated requests where I need to know the IP address of the analyzer. That's all taken care of by PCANT. Analyzer does its magic, publishes reports. We store those reports, and then when the user comes back, he can access those reports. So that's the general workflow. I'm going to show a quick demo, which will hopefully work. actually two demos. The first one, I'm actually going to show you minimal code so that you understand what we want the user to experience and what they need to know and what they don't need to know, more importantly. So the setup I have here is basically our gateway, our network equipment where we have our agent running. Two cameras. I only put one up on the board, but there are two cameras. And then my computer, which is accessing the platform being somewhere in Nokia Bell Labs. So first I'm going to show the observer code, and luckily this one's visible. From now on, all my slides are in dark backgrounds. So this is where we tell the network equipment how to extract data. And you'll see we don't really need to understand how it's doing that. We only need to tell it how to filter that data and how to extract what we need. So we have a parameter, which is the MAC address we want to filter traffic from. And for now, I'm just going to try and every second send the analyzer how much traffic from that MAC address I've seen in the past second. So I have an accumulator. And I basically just say, well, every time I start a capture, and every time I have a packet come in, I check the MAC address, grab its length, add it to the accumulator, and that's it. And every second, I just emit the size to the analyzer. What you'll notice here is I don't need to know how the analyzer is run, where it's run. I don't need to know how the packets are captured. This is something I don't need to be a network administrator to write. And that was the aim of the observer code. The analyzer code has basically the same idea. So here I have a very stupid analysis function which doesn't really do anything meaningful. But I will receive these messages that I was emitting at the observer, have a callback. Here that callback just appends the data to an aggregator list. And then every 10 seconds, I'm going to look at statistics, so the mean and the average, for example, on that data I've received in the last 10 seconds. Not very interesting idea. The only thing that's important is same thing. How I get the data, how I publish my reports are all taken care of by PCANT. I don't need to worry about the architecture behind that. I can write my code, and that's basically everything you have around that code. Is there a question? No? So basically, now we can focus on the machine learning part, and everything else is taken care of. There's a bit of extra code. So we saw there was a parameter, which is the MAC address I want to monitor, so that has to be provided as well. And if you're doing Python, you need to provide the requirements you'll have in terms of dependencies for your Python code. But that's it. That's all you need to provide, and then you push that to the platform, and your code is up and running on the network. So the demo. And here we hope it works. No. So I'm going to start with just the demo I showed you. So this is the interface. It's kind of hard to read. I'm going to create a blueprint. Oh, okay. So the blueprint for what I just showed you as code is going to be called the statistics blueprint. I'm going to upload the files I showed you in a tarball, and there are really only those 4 files. So when I do that, normally, hopefully it'll show up. If I didn't break everything in the meantime. Just checking. Oh, everything broke. So I'm going to try and bring things back up, but this may take a second. This is the problem with demos. Yep. All right, so again, create the blueprint. Yeah, so we've got the blueprint up. It's actually building. So you see at the right, it says not built yet. This is because it's installing all the Python dependencies. Here I just had NumPy, so it wasn't really a big deal. And the blueprint is ready. And now that that blueprint is ready, I can create a task. So that means instantiating that blueprint and providing a MAC address, which I will now retrieve. to be monitored. And now I have a task up. And that MAC address corresponds to the camera I showed you earlier. I really apologize for the people in the room who can't see anything on the screen. I start my task, and so now I'm looking for traffic in the network. As I said, I'm grabbing the traffic length every second, sending it to the analyzer who's calculating some statistics on that MAC address, on traffic from that MAC address, and publishing it. So if I go to the reports tab on the left, I should be seeing reports every now and again showing up. So for now, the problem with the camera is it starts very slowly. I should have started a bit earlier. It doesn't send traffic for like 30 seconds, so for now we're not seeing any traffic. But believe me, in a few seconds, hopefully, we should see traffic sort of pop up. I don't like the fact that it has a red power light, but we'll see.
It takes 30 to 1 minute.
Now it's green. Okay, hopefully it's talking. We'll see. Yep, so now we've actually seen statistics on the network flow. So not a very interesting task, but this is more to show how I don't have to do much to deploy that to the network. So I'm going to stop that. And I'm going to show you another blueprint. This one is the one created by Nesrine with Ludovic and Sébastien. And one of the things I want to showcase with this is that, one, we were able to adapt it easily to IoT&M. And two, since this is all working on a REST API, you can actually use IoT&M programmatically. If you have something else that wants to interact with it, run tasks automatically, you can run 50 tasks at once without having to click through the buttons and things like that. So in the case of, sorry, I'm just going to make sure, yeah, this works. In the case of this demo, I'm just going to get back to my slides if I can find them. So what is the demo about? Okay, I'm actually now on the screen for some reason. So what is this demo about? Basically, we're going to look at new devices in the network, so whose MAC address we haven't seen, capture their traffic for a minute, and analyze that traffic to sort of identify what type of device it is based off of a data set we've learned from earlier. So it's a machine learning algorithm that basically, yeah, uses a prior data set to extract that information about what devices are appearing on the network. I'm going to, okay. So one of the nice things is that for this demo, they had a nice UI showing what happens. And we managed to plug that UI into the API of PCANT. Okay. Into the API of PCANT. So now when I run the task, you'll see the UI update immediately. So I'm going to run that task. Device type I already created it because the blueprint requires loading scikit-learn, which takes a while actually to install. Especially if you use an old version of scikit-learn. So did I turn this off? Yeah. Yeah, we'll just plug both in at the same time. So we're plugging two devices in. And hopefully I didn't mess things up. Yep. We plug two devices in. And once they start emitting traffic, I think both of them are slow to emit traffic. Okay. Once they start emitting traffic, this UI is actually going to receive the reports from the analyzer, and it's going to start updating what it's showing on screen. So we have a first device that pops up. We don't know what it is yet. This means we have a new MAC address that arrived in the network. We've created a first report that says, I have a MAC address. The UI has caught that through the REST API. And the analyzer just started working on that 1 minute capture. Well, sorry, the observer is doing that 1 minute capture, sending it to the analyzer, and the analyzer is then going to infer what type of device it is. The second camera just popped up. So now I have to do filler text for 1 minute because it's a 1 minute capture. But yeah, once again, the important part here is really to see that whatever your solution, whatever the UI you want to put on top of it is, if you want to deploy it on a network, we have what it takes to put inside the network to have that up and running easily without you needing to really worry about it. Yeah, go ahead. I have a minute to kill, so go ahead.
Okay, this is one. So here, someone is taking some pickup capture. So
yeah,
who is this?
The agent inside here,
okay,
and the observer code I pushed.
Okay.
It's running inside here right now, and it's capturing that traffic. So here, the minute finished, and the analyzer set code said it's a camera, and I can actually show you it identified it as a Panasonic camera. So I think that's that one. And the other one we'll see is normally a D-Link, hopefully. Yeah, D-Link. Got the, so
yeah, and what are the requirements to run Linux?
Yeah. So this is the gateway we have here is running OpenWRT, and the complex requirement. So it is a Linux distribution for gateway, for user gateways like that. And we're running it through libpcap. I have this later on in the slide. What that means is libpcap is it's the low layer C library that's used by TCP dump and Wireshark. We're using that same thing to capture traffic. Performance-wise, we still have a few things we're trying to work out, because depending on if you're really capturing all traffic, it kind of slows you down. But that's things we're working on to look if we have solutions, or if we're just going to accept that if you want to look at all the traffic, then you're definitely going to slow things down. But yeah, the requirement is to be able to compile libpcap. I'll say a bit more about the agent, because as you saw, the code we're providing is Node.js code, snippets. So that's, I'll come back to that as to why.
But, I mean, continuing with this question, because I have
Go ahead.
If you look at the different type of devices that are in the market, wherever, for a box in the house, or for the core network, or for a telecom operator, today, how many which percentage of the devices you can deploy such a thing?
I can't give you like a percentage, because that's a bit of a no.
Roughly speaking, I mean, it's something.
I have a very biased view on this, because we only get equipment from the lab where we can work on them. So for me, all of them are workable with.
That's exactly my point.
I think in enterprise networks, if you start providing this is sort of a solution that would be provided by the network provider to the enterprise. So they would have to have compatible equipment. I don't think, we had a discussion recently with somebody in Nokia who said we have so much software today for updating the firmware on these equipment that if we really wanted to push this as a solution, and this is a prototype, but if you really wanted to commercialize it, you would have to look at the solutions which allow you to push firmware to these devices. I don't know to what extent something like libpcap is highly available. That's clearly a Linux solution. So I don't really know to what extent. We also wanted to look at smart NICs, smart network interface cards, to see what's doable at that level.
The reason I'm asking is that if you look to a specific vendor, they will have their own solution. What I think is very interesting in what they're saying is that it should run over whatever platform.
Yeah,
But it's not clear for me.
So there's one of the things I haven't gone into detail about. When I say user, this was really for more the data scientist. You still have the network administrator providing the network, which has to deploy it. And at that level, there's kind of a choice of how do I make sure I can monitor my whole network. I have to install it inside each network equipment. Vendors have specific solutions for providing software inside their network equipment, and you'd have to adapt for each vendor. Say, look, I have a generic solution. How do I adapt it to your equipment so that we can deploy it through firmware updates or something like that? I know one thing we've been looking at is the Beacon 6, maybe a possibility of trying to push this to one gateway we have at Nokia, where they have a modular architecture where you can easily deploy new modules, but we haven't really worked on that yet. So
what about virtualized solution? I mean, if you have an SDN controller, is there any API in SDN standards that you can ask such a thing to be driving?
Virtualization is often an issue because you get it at edge clouds, you have lots of solutions. Inside the gateways themselves, it's rarer. And here we really need to virtualize and capture. You can't really virtualize that low inside the architecture at the network interface level.
I think worded my question, you're right. But what I think is that if we, just to try to generalize the idea, right? Because again, I see a value when it runs over several platforms. It's not each vendor will tell you, as you said before, I have the right solution for that. Now, if you're talking about an SDN-based solution, if you can talk with the controller, which is control a different type of devices, then you have a bigger chance, right? If you can tell the SDN controller that you would like to see such a thing, and the controller will talk with the devices, maybe
I guess this is almost what we're doing. If you consider the platform as an SDN controller, basically our agents are connecting to that platform and say, what do I do? So this is that same philosophy. We have a controller somewhere telling them, here's the observer code you're running that'll tell you how to check data. We wanted to look at how can we push that into existing solutions for SDN. One thing we were looking at is P4 for programmable traffic, programmable networking, seeing if there's a solution to automate network captures through that, but we haven't had time to really get into the details. But yeah, this ties into an SDN approach where the idea is the way you monitor your network is clearly defined by software, the platform, which is really orchestrating all that. And I'll mention this in a bit. I don't know how much time I have left. There's a lot of work we still need to do, and this is where it's one of the 2 or 3 subjects we're looking into about what happens when I have lots of gateways, lots of network equipment, because traffic is passing through 5 of them. Do I want to capture at each one? Or if, in this case, I only need 1 capture, I don't need all 5. And so we've got all sorts of ideas about managing the network and the needs of the users in that network for them, orchestrating the capture. I only need these traces once, but one question we had recently is, if that traffic is going through 10 network equipments, can each of them grab 1/10 of the traffic? That way I have a much smaller network impact and performance impact on a given router. And this definitely takes orchestration at a higher level to really orchestrate between the agents. And so this is one of the ideas we had. We don't know how to do that yet because it's very use case dependent. But yeah, I'd argue we have a very SDN approach to the way we're thinking monitoring. I don't know if that answers the question, Jeff.
It does. I mean, the sub-question, the sub-item is whether the standards as they get today, which I don't know that well.
Neither do I.
Okay.
I haven't seen on the monitoring side. The problem is there are a lot of standards to monitor IoT devices using agents on the devices themselves. There's a lot of things to. We have solutions on network equipment to get float statistics, but these are used inside core networks where you really want just statistics and you don't want to impact the performance. So you only have jitter, throughput, things like that. If your algorithm needs something more, needs to do DPI, needs to, I don't know, look at the 15th bit, whatever, you can't do that because they're not that generic. They have very strict limit on what they provide as data.
这么直接就是。
I don't know of any standards that go in that sense at network level. For IoT devices, there are probably more things for monitoring IoT devices because that's more the trend today. Network-wise, I don't know of anything, but I may be missing out on something.
For example, netconf or SNMP, simple network management protocol. So what's the advantage of this with respect to this classic?
Last I know, so you said net.
One is netconf.
Yeah, which is a configuration. For me, it was configuration and not monitoring, but I may be wrong.
It gives you, I mean, I receive these packets per second,
yeah.
and then you can configure.
You get high order statistics. But if your algorithm requires something else, basically it's these statistics and nothing else. And it's the same thing as we've used SFlow, NetFlow, things like that. You've got all sorts of things that bring you data, but it's generally always the same statistics, and you're stuck with those. One of the key things in PCANT is we wanted users to be able to say, this is what I want to extract from the traffic, specifically.
I just want to add something. This example that is shown in this demo is the work of Nesrinama service. And in that case, what we needed at the time was the first packets, 1 minute of traffic, the first 1 minute of traffic when you have to connect. And from this, we get several information that is listed here. The MAC, the host name, user agent if it exists, UPnP if it exists, and so on and so on. So we need to go to pick up some different data inside the traffic trace that are not given by the network. So, and to do that, what we developed, we had a demo, but we developed a specific demo to that. And doing that, this is how I thought about this idea of having something more generic on which you can do what you want. This is the idea of UNM and PCANT.
An example using this use case, one of the things I didn't show in the code I showed, but we also allowed users to say, I actually want to interact with the device. The use case here was if the device's broadcast, is it UPnP? So there's none here, right?
No.
None of these broadcast UPnP, but we had devices which would do UPnP advertising, where basically they say, I'm a UPnP device. If you want more data, request this URL. And PCANT allows you to say, okay, then in that case, I want to request that URL. I'm pretty sure, I just checked both of them. I'm pretty sure none of them do UPnP. Otherwise, I could show you, because we have all the data.
Here you have MDNS. MDNS was passive.
Yeah, MDNS is passive. So it can get you a lot more data than the typical solutions, because the typical solutions have really that set of statistics. You're stuck with jitter, throughput, things like that. The downside, of course, is the impact on the network. Basically, we tried doing some measurement tests, some performance measurements recently, and running full file download at maximum speed. If we're looking at every packet, if we're just capturing every packet, even just requiring its size, which you could do at a lower level, so this is really a bad use case for PCANT, we're dividing traffic throughput by half, more or less. So it's a big performance impact. It's not the use case for PCANT, where we really want to have more leverage. We're looking into solutions to try and improve that, but it's really hard because you're giving users the access to all traffic. So there is a cost.
There's something I want to add also on this use case. So we developed a specific demo that we published in TMA 19. And here for this demo, in fact, I just reused the code that was developed by Nesrin, and I packaged it a little, but there was not a lot of work to do. So we use it directly on our platform. So this is really easy it was really easy to remove the code.
Okay, so that's for the demo, and I can move on if I know where my slides are. Yeah. So status of the project, I guess, at this point. So this is what the project actually looks like if you look at the platform architecture. I don't want to get into the details. I sort of showed a few managers like Task Manager and Blueprint Manager when I did the workflow earlier. But it's a microservice architecture with quite a few components and growing. The two things I want to mention. So I mentioned libpcap here for the observer agents. We rely on libpcap to capture the traffic. We've started thinking of, are there other solutions? We want to look at open vSwitches for sort of filtering at a lower level before we capture. I forget what the other things are we want to look into, DPDK. We have a few solutions we want to look into, but the more you look into those, the more it becomes engineering work. And this was really a proof of concept. We don't know what direction we want to push it in. As for the platform itself, it runs on Docker and Docker Compose for the whole box thing. Last thing I want to say, why Node.js? So all of those components are Node.js, including the observer agent running here. So currently this has to run Node.js, which is a big take. The real reason is this was a proof of concept, and this was the quickest thing to get into. We could deploy it in C, but it would take more time, and we wanted to get it to that level. The microservice architecture has one advantage, is that if I want to write this in C, I just write this in C, and the rest doesn't work. But we haven't gotten to that level of precision yet. And we've actually run some tests. The performance degradation isn't primarily due to Node.js. It's more the capture itself. So we wouldn't really gain at that level. This gateway is rather powerful for a home gateway, for example. If you really wanted to get the more smaller equipment, it would probably be more of an issue. But it's more a design choice as part of the research project. As for the rest, the analyzer framework is the only thing that's written in Python, because we want to provide Python for the machine learning code, obviously. The rest is in Node.js because it's a lot easier for all the asynchronous microservice architecture thing. So, and because it's what I was fluent with, to be honest. So that's basically the overview. I don't really want to talk about each item specifically because it's not interesting. Oh yeah, one last thing. The analyzers themselves, as I said, for example, with scikit-learn, we're downloading scikit-learn. When I provide a blueprint, I'm actually constructing a Docker image for that analyzer, and every time I start a task with specific parameters, I have one container. So we isolate everything. And this is important because going forward, one of the things we want to look into is multi-tenancy. I'll get back to that. But isolating the tasks one from another is something we're focusing on, and there are challenges. So possible improvements. The blueprint framework, so the code we provide to the user so that it's easier for them. As I said, working with multiple gateways is something that's currently a bit complicated. Basically, every gateway is acquiring all the traffic, and the analyzers are retrieving all that data from each gateway, and you don't always need that. Interactions with users, this is one that's kind of important for reinforcement learning. Sometimes your task needs user input. So it's easy to output a report that says, I need input, but we don't currently have a way of saying, while the task is running, I want to give it a special instruction. So that's one of the things we mean to look at. And that's about it. So this we actually have to a certain extent. We know how to do HTTP requests from the observer code for UPnP. We want to be able to provide arbitrary Ethernet traffic for now. And then other improvements, I spoke about task isolation, performance I spoke about, and then report reuse. So one of the things that's interesting when you start doing something where you can have lots of tasks running, learning things about your network, your devices and things like that, is we want certain tasks to be able to reuse others. So for now we have, for example, a task which identifies the type of each device. Maybe we have a task that wants to say, if I have cameras, I want to monitor more closely their traffic flow. To know what are the cameras, I'd have to use the output of the previous task. Currently, we have no way to sort of chain tasks, but that's definitely something we want to put into place, because it would make monitoring a fully modular structure in a network. And that brings me to multi-tenancy, which is really our main focus today, is both for shared infrastructures, but also for federated learning use cases. We want to ask ourselves, if I have either a big infrastructure that is shared or multiple infrastructures where people are doing their monitoring, how can they share data? How can they share the infrastructure? How can I manage multiple users, respecting privacy, security, and things like that? So currently, there are a lot of questions that we're still going through, but the core idea is for the shared infrastructures, devices have owners inside the system, and those owners are responsible for saying who can see what in the network. So we need to have a pre-filter in the network so that I can only see part of the traffic going through that gateway, and possibly using anonymization if I want others to see the traffic but not the MAC address, for example. And then same thing at the task level. If I have a task that identifies the device, will I allow somebody else to use those results, maybe part of those results, and how? So there's a lot of question about sharing information, exposing information I know about the network to somebody else while keeping tabs on who knows what and who's allowed to divulge, to show what, to share what for information. So this is currently what we're looking at, and it's kind of a mess, but it works fun. That's it for me. So do I have any questions?
Hi, I have one question about the agent part in your framework. I would like to know how many traffic capturing and measurement methods that will support, or how many traffic measurement algorithms that your agents can perform.
All right, so as I said, our agent doesn't actually provide a specific set of of measurement types. If you look at the code that's used to capture traffic, basically it's capturing every packet and asking this user code, what do you want to do with that packet? So I'd argue just about anything you can do from the packets.
Yeah.
Things currently you can't do include emitting arbitrary traffic. We can only do HTTP requests. That's one thing we're working on. Querying the network equipment itself for information. We were wondering if it was interesting, for example, if your gateway is running a DHCP server, to look at the DHCP leases, things like that. That we can't do with this framework. It's not hard to do.
Yeah.
It's just something we haven't gotten down to. But there's no, the key idea of genericity in this framework is that we're not making assumptions on what data the users want to extract from the traffic. We're trying to give them as much freedom as possible in that regard. Does that answer your question?
Yeah, okay. But I think in some, like in core networks or data center networks, it might be hard,
we have more focused on enterprise networks where network optimization isn't necessarily the key criteria, especially if you balance that with security, for example. We have had questions regarding core networks. It's kind of hard because in core networks, you're basically going to have to do some form of sampling if you don't want to break your network. One of the questions we've had recently, we haven't had time to look at, is I don't have a framework here which allows users to work on samples. It's something we definitely need to get at some point, if we have time, through, is allowing them to say, look, this is server code. It's okay if it only gets 10% of traffic. And that's probably the approach we'd have to take for something like core networks or data center networks. For now, the assumption is we're looking at every packet, which is a very heavy assumption.
Yeah, exactly. Thanks. And I have another question about the ML algorithm that you deployed on centrally, and about that, because the ML models usually their performance can degrade, over time because the data shift in the network, and if the quality of the inference of that ML model decreases, do you have some mechanism to monitor this and replace a more up-to-date model? You know, because you are dealing with a DevOps problem in your framework.
So for the one I showed, clearly we're working on a data set and an inference that dates back a few years. One of the questions we have is, I showed you the evaluation phase of the ML inference phase. We didn't show the learning phase. If you want to do, one of the things we've been thinking about is, can I do learning, live learning on a network?
Online learning, yeah.
Yeah, this is something that definitely needs user input, which is why I mentioned that at some point for reinforcement learning. And there's no, if you have, I'm thinking about your question. One of the tricky things in your question is, if I have a model that's inferring data,
yeah,
how do I know if that inference is right or wrong?
Yeah, or assume you know it's wrong. Maybe do you have any mechanism to replace a new model? You know, automatically. Yeah.
So, approach one: I stop the task, I create a new blueprint, and I run that blueprint. That's the cheap answer. If I have user input implemented, then I can definitely say one type of user input is, here's a new model. Right. So the solution to what you're suggesting would definitely be that user input approach, where if users can provide input live to a running algorithm, then yeah, there's no problem switching the model. But I think it goes further than that. One of the things we're looking at in PCANT is actually learning live on a live network.
Yeah,
you could have two models running on two different networks. Well, sorry, two tests running on two different models. Start again. Two tests running on two different networks. One of them learning, providing a model to the other, using that model to infer. And if you start looking at federated learning approaches, you can have this all over the place. And it's definitely something we would look at. We've also had questions about, considerations about, for example, if your ML approach has feature extraction at the start, would your feature extraction be done by the observer code? Because that sometimes could be rather quick. And if yes, can we update that live? And the answer is yes. Currently, analyzers can actually push data to the observer codes if we want to change the observation live. So this sort of mechanism, we don't have all of them, but it's definitely the sort of thing we want to put into place, because it's sort of one of the targets we have is to make all that possible, because it's definitely things that are desirable and that are hard to put into place currently.
Yeah. Thank you.
Yeah, I have another question. I'm online. So if I resume very badly what you just explained, you are presenting an abstraction for the traffic analysis in different kind of networks, and you are offloading the cost, as you mentioned, of this abstraction, in particular to the. So you are hiding this cost because you let users present their simple monitoring instructions with the JavaScript code, and I wanted to know. So this cost is hidden somewhere, right? Because I mean, for instance, if I go back to the separation between the network engineers and the data analysts, for instance, Tianzu and I, we worked on the network monitoring at very low level, so we were actually able to perform deep packet inspections on at line rate. Okay, so and we did not use a high-level programming language, right?
So I'll ask this question first. Your deep packet inspection, how did you capture the traffic?
We use the DPDK.
Okay. And DPDK is one of the things we need to look at in replacement of libpcap. Definitely something we know we need to look at. But if we replaced libpcap with DPDK, the truth is the Node.js currently isn't the bottleneck. Libpcap is. If we move to DPDK and Node.js was the bottleneck, then we'd have to recode this in C. We have ideas of making this more low level. This code I'm showing right now, one of our ideas, if we wanted to make it because.
So sorry, I interrupt you. I interrupt you because I'm not complaining about the high-level code. I'm actually happy about that. So I want code to be simpler. So there's value on it. So I wanted to see if there is a way to take the best of both worlds.
I'll try to answer that with what we have in mind, because I agree there's definitely a cost. For now, for example, we know that we're capturing every traffic and moving it to user space, every packet and moving it to user space. And if we had a more involved framework where we said, no, you have to tell us exactly what max you want separately, not in your code, we could move that to lower levels and gain in performance. So there is a cost. Obviously, at the capture level, as I said, traffic max throughput is currently divided by 2, basically. And that is the big cost of doing it this way. We're looking at ways to improve that. There will always be a cost. If you have a very specific need and you program it at a very, very low level, you have obviously an advantage that we won't be able to rival with. We have ideas to work through that. So DPDK was one of them. Using open vSwitches to filter traffic and then capturing only part of the traffic was another one. Distributing the capture throughout the network, you can capture a stream at different places. As far as the environment where we're running the observer code, moving away from Node.js is an obvious one. One of the hard parts is you want code that can be hot loaded. It has to be something which you can plug in and plug off without restarting the process all the time. So this was one of the reasons also we used JavaScript, because it was really easy to do that. But we have other ideas. One of the things we were looking at is WebAssembly, which once compiled can be loaded and unloaded really quickly, and which is pretty low level, which is the interpreter really quickly maps it to assembly code. So we have these ideas. Each of them will get us a bit closer to optimal performance. We won't ever get there. We won't work through all of them because time constraints.
Yeah,
it's
definitely
1.5 developers on this project. So,
sure. For instance, as a side note, if we go, I mean, I remember it was in slide 6 or 9. I don't remember when you were presenting the architecture. So we had also here. Okay, it's okay. So when you want, for instance, your analysis, right? So the scope of your work is to, I mean, you were talking about putting some traffic analysis or some machine learning more online, okay? So like in a live fashion. But here I see also a difference. So online, what does it mean for you online? Because here there's the cost of, I mean, the latency, if you want, of transferring the data to the compute, plus the latency of letting the algorithm run and spitting out an answer.
Yeah. Okay. So online was more, as opposed to what I was seeing earlier, where people were doing traffic capture, dumping everything in a PCAP file, porting it to another computer where they had their ML stuff and running it on the PCAP file. And then if you couldn't really do any control. So yes, there's a delay clearly in the transport to the analyzer, the analysis function itself. I'd argue that it's probably less costly performance-wise than trying to run the analyzer on the network equipment, where you'd have another type of delay. I haven't specified where the platform runs or where the compute node runs, because we've run it both in the cloud at Nokia, like it's doing now. We've run it on our computers locally. We haven't looked at actually distributing the compute node for a fog or edge cloud approach, which would probably be the right solution if you have performance critical machine learning. It's definitely something that's important, because one of the other projects I work on, Dispose, is one we may want to interface with, because they do more network control. And having the possibility of analyzing what's happening in the network and taking decisions for network.
Yes, it's not. I totally agree. And in fact, I mean, my question was if you have any numbers on that, because it depends on what you mean. Like, depending on this latency, delay, the answer may be very different. I mean, if it takes 1 second in network time and you're doing intrusion detection, 1 second, it's already too late, you know.
Right. There are two types of latencies. Currently, in terms of transmission, if you go back to the user code, here at the bottom, when I do analyzer.emit to send to the analyzer, I do it once every second. Mm-hmm. So there's that latency, obviously. But then it's the network. There's no extra cost. There's no like buffer. Well, there are buffers because we have a Rabbit MQ in the meantime. But it's pretty like if your constraint is the second, then you're fine. If you want to hit the milliseconds, then you're in trouble. But that would be sort of the thing. We don't have 10-second delays. Apart if your ML algorithm takes a minute, well, it really depends on what you put as the backend. If you
exactly. So that's why I was asking about the scope, because depending on the algorithm, it may be not different to detect an intrusion some seconds later than analyzing a pickup afterwards to do the.
One of the things we don't do for users is the trade-off between what you do on the observer and what you do in the analyzer. We haven't really looked at the performance at that level because it's so use case dependent, the requirements, that it's hard to say this is what we want to optimize. If you want really low latency responses, then PCANT isn't really optimizing that. But we have 1 second response times if you want to see something happen within the second, and you want to, like, if you want to block traffic to a device when you see something bad happening with that device, you'll have at most 1 second between the moment where that device is sending that traffic and it reaches the analyzer, and at most 1 second between the moment where the analyzer tells you it's bad and you can react. That would be the order. It's probably less than that. It's probably 100 milliseconds, but that would definitely be sort of the guarantee I would give you. We don't have bigger delays. There is, however, another delay is when you're starting and stopping tasks. If you want to be able to start a task really fast, here we're running Docker containers, so you actually have to do the set up the container, and that has a small delay as well. And even bigger delay when you're building blueprints, as I said. For scikit-learn, downloading a specific version of scikit-learn for that specific blueprint can take up to a minute depending on your network connection. Ours isn't the best.
Okay, thanks.
Yeah. Okay.
Thanks again.